Hello and welcome to another session of the Digital Forensic and Investigation. In the previous session, we discussed what is digital investigation, the process of the digital investigations, and what are the main phases involved in the digital investigation process. For example, identification, preservation, analysis, and presentation. And in the end of that session, we also discussed various approaches, examination approaches, for example, the time frame analysis, application and file analysis, ownership and possession analysis, and then data hiding analysis. In this session, we will discuss the hard drive internal structure, master boot record structure, and also its partition table. And then we will discuss the GPT basics. So let's begin with the digital data basics. So every digital data is a combination of ones and zeros. And those ones and zeros are commonly known as bits. So it is often necessary for the digital investigator to deal with those data at the bit level. And there is a need to understand that how the different system represents that data. So there are various formats that can be used to represent data, but the most commonly used formats are binary format, decimal format, and hexadecimal format. So the binary format consists of only two symbols, 0 and 1. And data in the binary format consists of a stream of those zeros and ones. In the decimal format, we have 10 symbols from 0 to 9. And data in the decimal format is represented as a stream of those 10 symbols. In hexadecimal format, we have 16 symbols 0 to 9 and A to F. The hexadecimal equivalent of A is 10 in decimal. Similarly, hexadecimal B is equivalent to 11 in decimal, and F is equivalent to 15 in decimal. Again, similar to the binary and decimal format, the data in the hexadecimal format is also represented as a stream of those hexadecimal symbols or digits. Okay, now each symbol in the binary format is called as bit, as I mentioned previously, and its value could be either 0 or 1. So these bits are usually organized in a group of 8 bits, and this group of 8 bit is known as byte. So as I said, a bit value could be either 0 or 1, so it means that a single bit can store up to two integer values, decimal integer values, 0 or 1. But if we have more than two integers, then we need to increase the number of bits. For example, if we use 2 bits, then we can create up to 4 different possible combinations with those two bits, where each combination will represent a unique decimal value. So with that 2-bit combinations, we can create 00, 01, 10, and 11 unique combinations. So 00 will represent a decimal 0, 01 will represent a decimal 1, 10 will represent a decimal 2, and 11 will represent a decimal 3. Similarly, if we increase bit combinations from 2 to 3, then we can represent up to 8 decimal numbers. Also, if we further increase the number of bits from 3 to 4, so then with the 4-bit combinations, we can create up to 16 unique combinations, and each combination will represent a unique decimal number. So in decimal, we can say that we can create 16 symbols ranging from 0 to 15. But if we speak in the hexadecimal format, so those 4-bit combinations can uniquely identify 16 hexadecimal symbols 0 to 9 and A to F. So for example, also if we have an 8-bit binary string, so we can easily convert that 8-bit binary string into the hexadecimal format. So to do so, we need to divide the whole string into 4-bit block, starting from right to left. and then represent each 4-bit binary block with its hexadecimal equivalent. For example, if we have a bit string of 100, 1 and then 310, so these are 8 bits in total. So after dividing them into 4-bit groups, so we are left with two groups, 1110 and 1001. So the hexadecimal equivalent of 1110 is E, while 1001 is equal to 9. So, and hexadecimal representation of this conversion will be as 0x9e. So 0x shows that the number is in the hexadecimal format. And we care about the hexadecimal numbers because they are frequently used, and when we will examine the hard drives and also the raw data collected during the evidence. And it can easily be converted uh, into the binary format and also the data from binary to the hexadecimal format. So a byte is the smallest amount of space that is typically allocated to a data. So as byte consists of 8 bits, it can be represent up to 256 values. And how those are calculated? These values are calculated as 2 raised to power n, where n represent the number of bits. So if we have more than 256 values or represent a larger value than the 256, then we need to combine again number of bytes. So here in the previous slide, we discussed that if we need more values, we combine number of bits. But in the hard drive, we combine number of bytes. And of course, those are combined in the form of groups like 1 byte, 2 bytes, 4 bytes, 8 bytes. Again, we follow the same rule, 2 raised to power n. So in this case, n represent number of bytes. Okay, so the way in which the bytes are arranged by the operating system is known as Endian. So we have two different types of bytes arrangements, Big Endian and Little Endian. In the Big Endian, operating system stores the most significant byte of the word at the smallest memory address and the least significant byte at the highest memory address. In Little Endian system, the operating system stores least significant byte at the lowest memory address. So both type of the arrangements are widely used in the digital electronics. So Big Endian is dominant ordering mechanism in the networking protocol, such as Internet Protocol Suite. So where it is referred to as like a network ordering and transmit the most significant byte first. On the other hand, Little Endian is a dominant ordering methodology in the processors architectures like x86 architectures, ARM implementation, or basic RISC implementation, and also with their associated memories. File formats can use any ordering system. Some format uses a mixture of both formats, Little Endian and Big Endian. The Intel x86 and AMD 64 series of all processor uses the Little Endian format, while, while the IBM architectures and also the Motorola architectures, they are using the Big Endian approach for storing the data. So here is an example of a data which will be stored at in the memory at location of 80, 81, 82, and 83. So the data actually consists of 4 bytes and the data value is 12BE6D33. And of course, these are like 8 hexadecimal numbers. So 2 hexadecimal numbers are used to represent 1 byte. So if we want to store this data into a memory location 80, 81, 82, 83 in the Big Endian format, so then 12 will be stored at the location of 80, BE will be stored at the location of 81, 6D will be stored at the location of 82, and 33 at 83 location. If we want to store the same data in the Little Endian format, in that case, 33 will be stored at the location of 80, 6D at 81, BE at 82, and 12 at 83. In case of binary representation, so let's consider again a decimal number which is 511, and its binary equivalent is 701 followed by 8 ones. If we want to store them in the big Indian format, so first we will store 701 at the lowest address and then 111 at the highest address. If we want to store the same data in the Little Indian format, then 8 ones will be stored first in the lower address and then 7 zeros and 1. So here you can see that we have reversed the order of the byte, not the bit inside the byte. So it is very important to consider that, to remember that the byte order will be changed, not the bit order. Okay, so a disk drive is a mechanism that reads data from the disk and writes data on the disk. So the disk in the hard drive rotates at a very high speed, and the heads in that hard drives are used to read and write data. So different types of hard drives uses different types of disks. For example, HDD hard drives accesses the hard disks. Floppy drives accesses the floppy disk, and optical drives accesses the optical disk. So those hard drives can be categorized into different types like fixed and removable. So fixed drive are those drives like hard disk which are not easily removable and which are mounted for forever like fixed. Removable drives are those drives that use media that can easily be removed from the system. For example, floppy disks, USB, CD-ROM, DVDs, even zip disks. So these are all different types of removable disks. In the hard disk, data is organized in a method which is similar to the filing a cabinet. So the user can easily access data and also programs stored on that hard drive. So when computer uses a program or data, it copies it from its location to a temporary location. So when user make changes to the file, the computer saves the modified file by replacing the old original file. So the hard drive you can see as an enclosure which contains a series of platters covered by a ferromagnetic coating material. And the direction of the magnetization represents the individual bits. So data is read and written by the heads, as I mentioned before, that moves extremely fast from one area of the disk to another area. Since all of these pieces are mechanical, the hard disk is the slowest component of any computer. So SSD is a newer type of disk which stores information on a flash memory, and that consists of the individual memory cell which store bits, and those bits are instantly accessible by the controller. So due to their non-mechanical nature, SSD requires low power, and which translates into a better battery life, and also these SSDs are shock resistant. So since, as I mentioned, that hard drives have moving parts, so if you drop your laptop, the chances are that the read and write heads of that hard drive, which is in motion, uh, are damaged and could lead to a data failure. But this doesn't apply to the SSD. So digital investigators need to understand that how persistent storage is organized and how data can be hidden on the hard disk so that it is not accessible via the file system interface. So as I said earlier that hard drive is an enclosure that contains a series of platters covered by the ferromagnetic coating. So these disk platters are round in shape and flat that hold the actual data. For an organized storage, and the retrieval of data, platters are divided into a specific structure. So both sides of the platers can hold a large chunk of the data that allows us for easier and faster access of the information. So each plater, as I mentioned before, has a head, read and write heads. So one is at the top of the plater and the other is at the bottom of the plater. So a hard drive with the 5 platers has 10 surfaces and 10 heads in total. So also those platers are further divided into tracks, and those tracks are like concentric circles on the plater where all the information is stored. So you can say a modern hard drive contains tens of thousands of tracks on each platers in order to increase the capacity. So each plater in the hard drive has the same track density, and the track density, you can say, refers to the compactness of the track circles. And manufacturer tries to increase the track density so that a maximum number of the bits can be stored on each of that plater and also each unit area of that plater surface. So the track density determines the amount of information that can be placed on a hard drive. Now, each track is divided into sector. So sector is considered as the basic physical unit of the hard drive that stores data. And each sector can hold 512 bytes of data with some additional information for the internal hard drive controls and also drive management and error detection and correction mechanism, and also for the sector identification itself. So sector is a basic physical unit of the hard drive. We also have clusters, and cluster is the smallest logical storage unit on the hard drive. So the file system divides storage on the disk into discrete chunks of the data for the efficient disk utilizations and performance. So these chunks are usually known as cluster, and a file is normally allocated a certain number of clusters each file. Okay, so a manufacturer designs a disk to have a certain number of sectors per track. And as I said, each sector stores 512 bytes. So to determine the total number of addressable bytes on a disk, multiply the number of cylinders with the number of heads, and then further multiply the output with the total number of sector. And this formula is known as cylinder head sector formula or cylinder head sector calculation. Tracks also follows the numbering scheme, which also starts from 0. So here is an example that how to calculate the capacity of a hard drive. So if we have total number of cylinders 16,384 and we have 80 heads and we have 63 sectors, so first we need to calculate the product of all these three, and that will lead us to capacity of that hard drive. And of course, the product of C, H, and S is further multiplied with the bytes 512 because each sector holds 512 bytes. So when you multiply all these factors, you will get a capacity of 42 gigabytes for that hard drive. File systems such as FAT32, FAT16, NTFS, extended to, and also UFS, which is used for the Solaris, they keep track of where the data are located on the disk and provide familiar information in a folder structure type of environment and feeling. So before the file system can be created, a partition must be created to specify that how much of the hard drive it will occupy. Okay, so the first sector on the hard drive contains a master boot record, which we call MBR, and it contains the partition table, which tells the operating system that how the hard disk is divided. So the partition table specifies the first and the last sector in the partition table. Okay, uh, in that partition, and in some addition, and also it provides some additional information about the partitions. The simplest way of viewing a partition is using the fdisk command on your system. So once the partition is created, it can be formatted with any file system. For instance, a fat file system can be created using a format command on Windows. The area occupied by the file system is called volume, which is assigned by a letter such as C by the operating system itself. The format command doesn't erase the data of the volume, so it is possible to recover the data from a hard drive after it has been reformatted. So if you compare a volume with a bookcase in a library, you will find that the file systems are similar to the library catalog, which provides an efficient way to locate a particular items in that shelf. So formatting a volume is like destroying the catalog order in the library by leaving books on the shelves without any order. So it is still possible to find a particular book, but it will take more time because the order has been destroyed. Also, the first sector on each volume is called boot sector, also known as boot record or boot block, and it contains important information about the file system. So the size of the disk sector is usually fixed by the manufacturer, but you can also specify the file system block size when you will format that hard drive. And the file system block size is again a multiple of that's each sector, like, and each sector size is 512. So you can select the block size equal to 512, or you can select a block size equal to 1024 bytes, which is actually two equal to two sectors. Also, you can increase to 4096, which is equal to eight sectors, and that block is actually known as cluster. And as I said, cluster is a logical smallest unit on the hard drive. So there are several features of the file systems that are useful from a data recovery perspective. When a file occupies less than one cluster, other files will not be able to use the remaining space in that specific cluster. So you can, in short, I can say that a cluster contains the data. Once if it contains the data, so the entire cluster is reserved. Okay, and this is similar to the situation in most restaurants, for example. So if three people are sitting on a table that's has like a capacity of 4 person, the fourth seat will remains empty until those three people have finished using that table. So there is a possibility that a fourth stranger might interfere with these three people's meal. So similarly, if a computer tries to squeeze that extra data into an unused space or the part of that cluster, so the new data might interfere with the old one in that specific cluster. And usually this unallocated or the extra space in that cluster is known as slack space. So we can say that the slack space is that area of the cluster which is left empty between the end of the file location and the end of the cluster location. If the size of a file is less than the cluster size, a full cluster is still assigned to that specific file. The remaining space remains unused and is called slack space. For example, if we have a cluster size of 1024 bytes, and a file size of only 24 bytes. So only 24 bytes will be stored, and the remaining 1000 bytes will be empty and will be known as wasted and also known as slack space. So slack space is not something which is similar to the unallocated space. So slack space is different from the unallocated space. So each time when a computer is turned on, it tries to familiarize itself with its internal component and also with its peripherals. So this startup process is known as boot process. And the boot process has three basic stages: CPU, central processing unit, power on self-test, post, and disk boot. So a CPU is considered as a core of any computer. So everything depends on the CPU's ability to process instructions that it receives. So the first stage in the boot process is to get the CPU started with an electrical pulse. And this electrical pulse is usually generated when the power switch or the button is activated, but can also be initiated over the network on some systems as well. So once the CPU is reset, it starts the computer's basic output system, which is also known as BIOS. So BIOS deals with the basic movement of the data around the computer. So every program runs on the computer system uses the BIOS to communicate with the CPU. Some BIOS programs allow an individual to set a password, for example, and until the password is typed in, the BIOS doesn't run and the computer doesn't function. So BIOS contains a program which is known as POST, Power on Self-Test, that tests the fundamental component of a computer. So when a CPU first activates the BIOS, the POST program is initiated. On a safe side, the first test verifies the integrity of the CPU and the POST program itself. The rest of the POST then verifies that all of the computer components are functioning properly. It includes the disk drives, monitors, RAM, and the keyboards. If there is a problem at any stage in the POST, the computer will emit a series of beeps and sometimes possibly error message on the screen. So when all hardware tests are completed, the BIOS instructs the CPU to look for a disk that contains an operating system. So then there is a disk boot. So the operating system extends functionality of the BIOS and act as an interface between the computer and the outside world. Without operating system, it would be very difficult to interact with the computers. And most computers expect an operating system to be provided on a floppy drive or on a hard drive or even on a compact disk. So when a computer is ready to load an operating system, it looks for these disks in order specified by the boot sequence setting. So a computer always loads the first operating system it finds. This fact actually allows anyone to prevent the computer from loading primary operating system by providing an alternate operating system on another hard drive or disk or USB. So for instance, a floppy disk contains an operating system that can be inserted into an Intel-based computer to prevent that computer to start the operating system to start from the hard drive. Okay, so this ability to prevent a computer from using an operating system on the hard drive is very important when a disk contains an evidence. So digital investigators should not attempt to perform such actions on evidential computer unless they are familiar with the particular types of the system. The master boot record is the first sector of the data store device or any storage device on the hard disk, as I mentioned before in the previous slides. So MBR is also known as a partition sector or the master partition table because it includes the table that contains the information about each partition within that hard drive. So in addition to this table, MBR also includes a program that reads the boot sector. So the boot sector is that sector of the storage device that contains code for bootstrapping a system. And bootstrapping is a process by which a small program initializes the operating system installed on that computer on that system. So the information about the files present on the hard drive, their location, their sizes is all contained in the master boot record file. So in DOS and even in Windows operating system, a user can create an MBR with the fdisk command. So the MBR is used to bootstrap operating system and also holds disk partition table information. So as you can see in the figure, the bootstrap code area is mentioned over there, the first area. Then we have the partition table area in the MBR, and then we have the boot record signature or the magic number area in that MBR. So that also the table includes further details about their location within within the sectors And this information is very critical to correctly analyze that MBR and on that hard drive. So as I said, bootstrapping code is responsible for to initiate the operating system. So it includes the activities like scan the partition table for active partitions, find the starting sector of the active partition, load a copy of the boot sector from the active partition into the memory, and also transfer control to the executable codes in the boot sector. So the if master boot record code cannot complete these functions, so the system displays one of the error message like invalid partition table or error logs or invalid operating systems or sometimes like missing operating systems. The third part of the boot of the MBR is the boot record signature. So that boot record signature is also known as the magic number, and it is a 2 byte of code, and it acts as a signature for the MBR. And it is usually located at the location of 1FE and 1FF. And its value is constant, which is 55 at 1FE location and AA at 1FF location. And both of those values are in hexadecimal. So to confirm the boot record signature in our system, read those 2 bytes starting from the offset value of 1FE using the hex editor, which you can use in, of course, you will be using in any forensic activity. Okay. So this is the output of a hex editor by examining the hard drive image. So here the first column represents the offset values of that table, hard drive table. Then we have the row with the values starting from 0 to 9 and then 1 to F. These are represents also the columns, and we'll add with the offset values to represent each particular value in that table. So for example, 0 in the offset column, the first no, the least significant, I would say, the least significant digit 0, which is hexadecimal, that represents the first column. If it is 1, that represents the second column, and of course the second value of that in that row. So if we have to go to the 55, which is located at the location of 1FE, so of course first you need to check the offset values, which is starting from 1F0. So that row is starting from 1F0. And if you go to the 1FE, so you will find that the value is at 1FE is 55. Okay. Of course, when you move the cursor to that position, so you can find the offset value at the bottom of that hex editor, which will tell you that where is the cursor at this particular point. So in order to locate the MBR disk image, again, you need to read those offset values at location of 1FE and 1FF. And when you will read that, so you will find that the values are 55 and AA. Okay, so as I said, the magic numbers both are located at the location of 1FE and 1FF. To investigate the master partition table, read between the two offset values. One is 1BE and the other one is 1FD. So the partition table location information is always available between these two offset values. The standard partition is limited to up to 4 partitions. However, the last partition can be used as an extended partition to include or support further partitioning of the table of that hard drive. So to investigate each partitions further, it is better to highlight them with the background color for the better view. For instance, I highlighted the bytes between the offset values 1BE to 1CD in the blue and applied similar approaches to the other values like pink color, other colors, okay? And also those values are represented in the table format here that The first partition table starts from 1BE, ends at 1CD. The second partition table starts from 1CE, ends at 1DD. Third partition table starts from 1DE, ends at 1ED, and so on. So both MBR and extended boot record use the same general format for entries in that partition table. So since disk editors often display 16 bytes per line, starting from with the offset values of all zeros, and the partition table begins at the offset value of 1BE within that sector, so it is very likely that you will see the entries overlapping each display line. For example, here is a simple single entry MBR partition table where the first column represents the offset values of each 16-byte line, and we have a bytes of data represented in the hexadecimal format, which is followed by the ASCII characters presenting each of these hexadecimal byte. So each 16 bytes of the partition table gives us more information. For example, the first byte represents the boot sector. In this case, if it is 80 hex, so that shows that the partition is an active partition. If it is 00, it means the partition is not an active partition. And then the remaining three partition, as you can see, they are starting with the value of 00. So it represents that the remaining three partitions are non-active partitions. Some boot managers might allow the logical partition to be set active, but more likely a boot manager will never use this indicator when they are doing like arranging the partitions. The next three bytes represent the starting sector in cylinder head cluster values. These values pinpoint the location of the partition's first sector on the hard drive. Next one byte represent the partition type descriptor. So it is a single byte allowing up to 256 possible values to indicate the type of the partition that can exist under the basic disk partitioning system. So for example, if it is 0B, so that will indicate that the partition file system type is FAT32. Next 3 bytes represent ending sector in the cylinder head cluster values. Next 4 bytes represent the starting of the sector, which is actually 4 byte, and this value uniquely identifies the first sector of a partition just as a starting of the cylinder head cluster value does. Okay. The next 4 bytes represents the partition size in terms of total number of sectors. Okay, so that again, when you calculate that value, so you need to multiply that value with the 512 bytes to know the size of the hard drive. Okay, so these 4 bytes represents that a maximum size of the MBR partition is 2 terabyte. It cannot be more than 2 terabyte. So these bytes values are stored on the hard drive in a little Endian fashion. So MBR does have some limitations. So MBR only works with a disk up to 2 terabyte, as I mentioned in the previous slide, that it contains only 4 bytes to calculate the size. So it can address up to 2 terabyte addresses. MBR also only supports up to 4 primary partitions. If you want more, you have to make one of your primary partition as an extended partition and create logical partition inside it. So MBR has some limitations. Master boot record and GPT, which is a GUID partition table, are two different types or are two different ways of storing the partition table information on a hard drive. This information includes where partition starts and where it ends. So your operating system knows which sector belongs to each partition and which partition is actually a bootable partition. So this is why you have to choose MBR or GPT before creating a partition on a hard drive. So GPT is a new standard that is gradually replacing MBR. It is associated with the UEFI, which is known as Unified Extensible Firmware Interface, which replaces the old BIOS with something more modern. Okay, so GPT replaces the old MBR partitioning system with more modern system, and it is called GUID partitioning table because every partition on your drive has a unique global identifier, and also, or you can say, a very long random string that every GPT partition on the earth can have, and of course, it will be a unique. So MBR uses a 32-bit addressing scheme. So if it is using 32 bits, so 32 bits is actually 4 bytes, so it can address up to a maximum of 2 terabyte size. While GPT uses a 64-bit addressing scheme, and because of that, 64-bit is equal to like 8 bytes, and they can address up to 8 terabyte addresses. So the maximum size of the hard drive of a partition in the GPT is 8 terabyte. As you have known that the partition information is stored directly in the master boot record, MBR also stores the information for loading the operating system uh, uh, about the bootstrapping, as I mentioned earlier. But the GPT hard disk, in the GPT hard disk, the partition table location information is stored in the GPT header. But for the compatibility reasons, the first sector of the hard drive is still used as an MBR, and after that, there is a GPT header. So, like the traditional MBR, GPT also uses the logical block addresses, which is known as LBA, instead of their early cylinder head clusters addresses. So the traditional MBR information stored in at the location of LBA0, while the GPT header is stored at the location of LBA1. The next partition table is stored itself. So a 64-bit Windows operating system uses 16,384 bytes, or you can say 32 sectors for the GPT partitioning table. Okay, so the first partition on the hard drive starts with the location at the location of LBA 34. So the partition itself starts from 34. Before that, there is information of the partitioning tables, entries, and also the GPT header and also the MBR location. So the partition style of the GPT disk is known as you can see in this slide. So LBA 0 represents the first MBR location. So we also have the secondary GPT. So secondary GPT is a backup of the primary GPT. So if the primary GPT partition table is destroyed for any reason, the secondary GPT will be used in that case. So at the beginning of the GPT partition table, for safety reason, it stores a traditional MBR partition table. This is because the hard disk, the disk management tool doesn't support the GPT, and it can destroy the data unexpectedly. So to stop the disk management tool from destroying data, a traditional MBR partition is used, and this is normally called as proactive MBR. And this is used to store the startup code for the operating system, which supports the GPT boot disks. The size of the GPT entries varies. After fixed header of 1024 bytes, the partition entry array describes partitions using a maximum size of 128 bytes for each entry block. So the starting location of the array on a disk and the size of each entry are given in the GPT header. Partition entries are simple and usually are done with equally incremented addresses. So the first 16 bytes are used to define the GUID partition type. The next 16 bytes contain the GUID that is unique to the partition itself. After that, there is a record of start and end of 64-bit LBAs, logical block addresses. The rest of the space is dedicated to the names and attributes of the partitions. The partition entry array starts from the starting location at LBA2. The actual partition starts from LBA34. As we saw in the previous slide, LBA0 holds proactive MBR, LBA1 holds GPT header, and then LBA2 to LBA33 means 32 blocks are used to store the partition entry array, and each block size is of course 512 bytes. So the total size of the partition entry array is again equal to 32 blocks, which is equal to 16,384 bytes. This table shows the GPT header format. So the GPT header, which has a standard size of 92 or 512 byte, contains the information shown in this table. For example, first 8 bytes represent the signature, next 4 bytes represent the revision, next 4 bytes represent the header size in the Little Endian format, and so on. So GPT has some advantages. So GPT doesn't suffer from the MBR's limitations. So GPT-based drives can be much larger, and its size limits depends on the operating system itself and its file systems. So GPT also allows for a nearly unlimited numbers of partitions. Okay. Again, the limit here will be from the operating system. So Windows allows up to 128 partitions on the GPT drive, 128 partitions. And you do not have to create an extended partition to make them work. Okay. On an MBR disk, the partitioning and boot data are all stored in one place. So if the data is overwritten or corrupted, then we are in trouble. But on the other hand, GPT stores multiple copies of this data across the disk. So it is much more robust and can recover if the data is corrupted. The one copy of the data is corrupted. GPT also stores cyclic redundancy CRC values to check if the data is intact. Okay. If the data is corrupted, GPT can notice the problem and attempt to recover the damaged data from another location of the disk. MBR had no way of knowing if its data is corrupted. So you would only see that there was a problem when boot processing fails and your drive partition is completely vanished. The MBR, which is a master boot record partitioning scheme, which is widely used since early 1980s, has some limitations. So, and a major deficiency is the limited size of the block, like 32 bits for block addressing, and also for the related information. So for a hard disk with 512 byte sectors, the MBR partition table entries allows a maximum size of 2 terabyte as discussed in the previous slides. And since GPT uses 64 bits for the logical block addressing LBA, allowing a maximum disk size of 2 raised to the power 64 sectors. And for disk with 512 bytes, the maximum size in the GPT is much larger than the MBR. So this brings us to the end of this session. So in summary, we saw that what is the digital data basics, how the data is represented. We also saw the basic internal structure of the hard drive. We also saw the MBR and partitioning table within that MBR. Also the GPT schemes, how the data is managed, and what is the header, and what is the role of the MBR in the GPT schemes to protect the operating system for crashing any valid data, destroying any valid data. Thank you for listening.